Okay, another thing that can be explained with the new model, the atom, is some of these subtle trends in ionization energy. So I'm not talking about the overall trends that we talked about last year, that if you had your periodic table, as you go this way, ionization energy goes up, and as you go this way, ionization energy goes up. That's not what I'm talking about. I'm talking about some of these subtle little trends like this one right here, where the atoms don't appear to follow the trend. And if we look at these and we look at them closely, now that we have a bit of an understanding about the rule where we talk about how half and full shells, or half and full sets of shells, are a little more stable, we can understand some of these subtler trends in the periodic table. So let's take a good look at where this trend is occurring. So we're going to talk about that one first. So first of all, we're dealing with the row that goes lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Okay? And what we see, if we imagine our filling shells here is 1s1, or sorry, not 1s1, 2s1, 2s2, 2s2, 2p1, 2s2, 2p2, 2s2, 2p3, 2s2, 2p4, 2s2, 2p5, and 2s2, 2p6. So let's just star the atoms that have the localized highest ionization energies. And so what we can see is that these atoms are corresponding to when the subshells are either full or half. So for example, beryllium has a slightly higher ionization energy than we would have expected because that 2s2 shell is full, and we actually get a lower ionization energy, so this one is lower, when we have to start our new shell. Similarly here, we have a higher ionization energy and a lower one here, right? So this trend goes up, and then there's a hiccup, and then it goes up again, and then there's another hiccup. That's this one right here. And that's because this shell is half full, and here we have to start adding, or we have to put a second electron in one of our p shells. Now we can say that this hiccup happens because when we have to put that second electron in, we're looking at having some electron-electron repulsion for the first time. Or we can say somehow this half full shell is a little stabler than when we start a new shell, and as a result the ionization energy associated with breaking up this half shell is higher than we otherwise expected it to be. And then our trend goes up as we expected until we get to our complete full shell, which is our maximum, and then we have to start a complete new energy level, or a complete new principal quantum number, and we drop right back down again to somewhere down here. One more time, let's talk through these, but let's do it using the energy level diagram. So, lithium has 1 in the S, beryllium has 1s, 2s. Here we can see with our subset full, we have a slightly higher level of stability than we would have otherwise expected. Starting a new shell, our stability actually lowers, or our ionization goes against the trend we expect because we lose that outermost shell being a completely full shell. Then we add 1 electron to each. We get to our half full state. Now we're up to nitrogen, and we can see that we have a slightly more stable situation than we otherwise would have. And then when we add 1 more electron, whether it's because of electron-electron repulsion or whether it's because we're breaking up this half shell configuration, we actually end up going to a slightly lower energy state where it's slightly less stable, a slightly higher energy state where it's easier to take electrons away. It has a lower ionization energy until we get all the way through to the end where we're very stable with our full electron shells before we start our next one up here. And we go back to a situation with a high amount of shielding and very little attraction for that electron. So, examining the subshells explains why we have some of the irregularities that we see in ionization energy. The overall trend is discussed in other videos, and if you want to go back and talk about the overall trend of ionization energy or the definition of ionization energy, you can go look at those. But here, we're just looking at why we have some of those funny trends that we didn't quite expect. We can see them again in the period 3 right there. So, our new model of the atom not only predicts the overall structure of the periodic table, but also helps us understand a few specific things about atoms and why some of the funny behavior that we're observing is happening.